All right, in this podcast, we're going to talk about electrochemical cells, which is basically galvanic cells is a name for them. You might also hear voltaic cells. Okay, so just understand that galvanic cells and voltaic cells are the same thing, and they are a type of electrochemical cell. All right, so in a redox reaction, we have transfer of energy. That energy is transferred through electrons, such as in the case of electricity, or through heat. So what happens when we place zinc metal in a copper sulfate solution? Okay, well, hopefully the first thing that comes to mind is that this is an ionic compound, this copper sulfate, and so it is going to split into ions. Okay, and so we're going to have copper 2 plus, and essentially what's going to happen is the copper is going to oxidize the zinc. So copper is going to gain 2 electrons, and zinc is going to lose 2 electrons. Okay, so we end up with Zn2 plus and regular copper. Okay, now understand that your SO4 2 minus is still just hanging out in solution. In this case, it is a spectator ion. Okay, so at the molecular level, this is basically what's happening. So we have our zinc metal here, and it is in our solution that contains our copper 2 plus ions. So these little these little gray atoms here are zinc solids. And the copper 2 plus is in solution. They come over here and they attach onto the metal. When they do, 2 electrons are transferred to the copper, and the zinc is then going to become Zn2 plus. Because it is charged, it is now aqueous, which means it's dissolved in a solution. Because the copper gained the 2 electrons, copper now goes to its normal state, which is a solid. So it's actually what we call plating onto here, okay? So the zincs are leaving and the coppers are taking their places, essentially. Okay, so when substances that are being oxidized and reduced are present in the same solution, the electrons are directly transferred when the reactants collide. Therefore, no useful energy is being obtained from the chemical energy that's involved in the reaction. So all of the energy is being released as heat in the solution. All right, so how do we harness this chemical energy from a redox reaction? Well, you have to separate the species that are being oxidized and the species that are being reduced. So we're forcing the electron transfer between the oxidized and reduced species to travel through a wire. Because it is traveling through a wire, the electron is traveling through a wire, it is producing a current, which we can then direct through a device such as an electric motor, which is going to provide us with some useful work. So we're going to basically take our chemical energy and we're going to put it to work. All right, so along comes galvanic cells, also known as voltaic cells. A galvanic cell is a device that transfers the electrons from one reactant to another through a pathway, such as a wire, as opposed to direct transfer like we saw before when we put those 2 substances in a beaker together. Galvanic cells are always going to be spontaneous or thermodynamically favored reactions, which means that our Gibbs free energy, or delta G, is always going to be less than 0. And we are taking that chemical energy in a galvanic cell and we're converting it into electrical energy that is moving the electrons through the wire. Okay, so here is a picture of a galvanic cell where we have copper and zinc metals and their solutions. Okay, so a couple things I want to point out. All right, over here we have a copper sulfate solution, And this right here, this copper electrode, it's solid copper. Then we have a wire, and notice that the wire is hooked up to a voltmeter, which is going to measure the current that is conducting through the wire. And the wire continues to a zinc electrode, so this is solid zinc over here, that is in a zinc sulfate solution over here. And then we have this little weird U-looking thing that is connecting our copper cell and our zinc cell, called a salt bridge. All right, so galvanic cell is only going to be spontaneous redox processes, which means that there is a positive cell potential and a negative delta G. All right, here's a super complicated look at a galvanic cell. We're going to get into all the specifics of this later, but I just wanted to kind of give you an idea of where we're headed.